Welcome to the deep dive.
Okay, so this idea, the unified field theory, trying to tie everything together in one neat package. It's the holy grail for physicists, right?
Yeah, that's been the dream for, gosh, almost a century now.
And you, our listener, you actually sent us an article looking at a recent attempt, or rather, a review of one.
That's the one. It's by Sabine Hossenfelder called Unified Field Theory. Physicist Reviews a Dubious New Claim.
Dubious. Okay.
Yeah, and that's what we're diving into today. We want to unpack her analysis, figure out why she uses that word, dubious. It's a great window into how science actually gets stress tested.
Definitely. So, okay, unifying forces,
Yeah.
gravity, electromagnetism. This isn't exactly the first time someone's had a crack at it. There's history here.
Oh, absolutely. Way back, I think 1920s, there was the Kaluza-Klein theory.
Kaluza-Klein, right, I've heard of that. Involved something pretty wild, didn't it?
It did. An extra spatial dimension. Tiny, curled up, supposedly.
An extra dimension.
Yeah.
Ugh. Yeah, and the amazing thing was, using that fifth dimension, they could write down equations that looked like both Einstein's gravity and Maxwell's electromagnetism. Pretty neat mathematical trick.
Okay, so if it was so neat, why aren't we all using Kaluza-Klein theory today? What was the catch?
Well, the catch was the particles,
Mm-hmm.
electrons, things with actual charge. The original theory described the forces okay, but it didn't really have a good way to include charged particles naturally.
Ah,
Yeah, trying to shoehorn them in later just led to more problems. So brilliant idea, but it kind of hit a wall when it met the reality of, well, matter.
right. Didn't quite map to everything we see. So, okay, fast forward. This new paper Hossenfelder is reviewing, they ditched the extra dimension idea.
They do. They take a different route.
Hmm.
They start with Einstein's general relativity, but an extension of it called wild gravity.
Wild gravity. Okay.
And the key thing is this wild gravity framework already includes an extra bit of mathematical machinery, a vector field, woven into the geometry of space-time.
So the hope is that this extra vector field can maybe do double duty, handle gravity and electromagnetism.
That seems to be the idea, yes. Can this extra mathematical lever account for both forces?
All right, so that's the setup. Wild gravity plus this vector field. But Hossenfelder calls it dubious. Where does she start poking holes in it?
Well, she starts right at the foundations, basically asking if the mathematical toolkit is even up to the job.
What do you mean?
She points out this thing called degrees of freedom. Essentially, how many independent knobs you have to turn mathematically to describe something. And she argues that just adding this one extra vector field, it probably doesn't give you enough independent knobs to fully describe both the electromagnetic field and the charged particles that interact with it.
Okay. Like trying to paint a detailed picture with only one brush.
Sort of, yeah. You might get the broad strokes, but
Right.
you're missing the nuance, the detail. It suggests a potential mismatch right from the start between the complexity of what they're trying to describe and the tools they're using.
Not enough tools. Okay, what's criticism number 2?
This one's pretty significant. It's how they try to incorporate electromagnetism. They essentially embed the electromagnetic potential directly into the metric tensor.
The metric tensor, that's the core thing in general relativity that describes space-time geometry, gravity.
Exactly. Tells things how to move, defines distances, and they're trying to weave the electromagnetic potential right into that fundamental structure
And Hossenfelder says that's a problem
because of the physical implications.
Yeah.
I mean, think about it. If electromagnetism is part of the actual geometry of space-time described by the metric,
everything would feel it.
precisely.
Yeah.
Even particles with no electric charge, like neutrons, they'd interact with electromagnetic fields according to this theory because they interact with space-time geometry.
But they don't. We know that. Neutrons fly straight through magnetic fields.
Yes, it's a direct contradiction with, well, countless experiments. So the very way they're trying to unify the forces seems to build in something non-physical from the get-go.
Wow, okay. That's a pretty big hurdle. What about the equations that come out of this setup? Do they look like standard physics?
Not really. This is another major point Hossenfelder makes. They derive an equation they call a generalized Maxwell's equation. Maxwell's equations are, the bedrock of classical electromagnetism.
Right. Learned those in physics class. Very successful.
Incredibly successful. And crucially, they are linear equations.
Okay. And the equation these authors get?
It's quadratic.
Okay.
It has terms where the electromagnetic potential is multiplied by itself.
Quadratic versus linear. Why is that such a big deal?
Well, linear equations behave in very predictable ways that match what we see with electromagnetism, like waves adding up simply. Quadratic equations, They often lead to much weirder, nonlinear behavior.
And does their equation at least simplify to the normal Maxwell's equations sometimes, like in certain situations?
That's the key point Hossenfeld makes. There's no limit, no approximation where their quadratic equation turns into the standard linear ones we know and trust. So it's not really generalizing Maxwell's equations.
It's just a different theory altogether.
Pretty much. A different theory that makes different predictions about how electromagnetism should work. Predictions that don't seem to match reality.
Okay, so the core concept seems shaky. The main equation doesn't match established physics. Does it get worse?
Unfortunately, yes. Hossenfelder points to issues with the basic mathematical techniques, specifically repeated mistakes in how they handle tensor indices.
Tensor indices. That sounds technical, like typos.
It's a bit more fundamental than just typos. Tensor calculus is the language of general relativity. Those little up and down indices, their placement, how you combine them, it's like the grammar of that language. Getting it wrong means your mathematical sentences might not make sense, or they might say something completely different from what you intended.
So it suggests maybe a misunderstanding of the very mathematical tools they need for this kind of theory.
That seems to be Hossenfelder's implication, yes. It's like trying to write complex code with fundamental syntax errors.
Ouch. Okay. What else? There was something about how they defined electric charge.
Right, charge density. This is another really strange one. Their definition involves multiplying the electromagnetic potential by the particle's 4 velocity.
Okay. And the consequence of defining it that way is?
The consequence is bizarre. It means a particle's electric charge isn't a fixed fundamental property anymore.
Wait, what?
Yeah. According to their definition, an electron's charge, for instance, would actually change depending on the strength of the electromagnetic field it's flying through.
That can't be right. We know the charge of an electron is constant, right? It's fundamental.
Exactly. Every experiment ever done shows the electron has a specific, unchanging charge. This definition completely contradicts that basic fact of nature.
So another direct conflict with observation.
And not just observation, it also violates something called gauge invariance.
Gauge invariance, remind me.
It's a deep principle in physics, basically saying that the underlying physical reality shouldn't change just because you choose a different but equivalent mathematical way to describe it. Like measuring temperature in Celsius or Fahrenheit, the actual heat is the same. Their definition of charge isn't gauge invariant, which is another serious red flag in fundamental physics.
Okay, wow. It seems like the problems are piling up. Foundational issues, equation issues, definition issues. Did she mention anything about the steps they took in their derivations? Any specific mathematical slips?
She did. She highlighted one particular step where they have a quadratic equation, and they try to simplify it by essentially dividing both sides by a vector.
Dividing by a vector. Can you even do that?
Not really, no. Not in this context. It's mathematically invalid. You lose information, you lose potential solutions. She gives a great analogy. Imagine you have the equation $32 plus $52. It's true, right? 9 plus 1625 will equal 0.
Yep, makes sense.
But you can't just divide that equation by the vector, 3, 4, 5, and expect the result to hold or make sense in a general way. It's a fundamental algebraic mistake applied in a much more complex setting.
Got it. That analogy makes it clear. So a basic math error in the middle of the derivation.
Seems so. And there's one more really big consequence of their theory, she points out.
Okay, what's the final nail in the coffin, so to speak?
It implies that all electric charges must move at the speed of light.
All of them. Always.
According to the structure of their theory, yes.
But that's obviously not true. Electrons moving in a wire, protons in an accelerator. They move at all sorts of speeds, usually much slower than light.
Precisely. Think about the electrons drifting in the wires, powering the device you're listening on right now. They're moving incredibly slowly compared to light speed. So this prediction is just wildly incorrect. It fundamentally breaks with everyday reality.
So let me try and sum up Hossenfelder's view then. It sounds like she's saying this paper has fundamental mathematical errors.
Yes, in tensor calculus and algebraic steps.
It introduces concepts, like the charge definition or putting EM in the metric, that lead to non-physical consequences.
Right, things that contradict direct experimental evidence.
And the core equations derived don't actually reproduce the known laws of electromagnetism.
Correct. They don't reduce to Maxwell's equations.
So basically, it doesn't work mathematically, and it doesn't work physically.
That's a very good summary of Hossenfelder's critique, yes. Her conclusion is pretty blunt.
What does she say?
She suggests the paper probably shouldn't have passed peer review, and given the number and nature of the errors, might even need to be retracted.
Wow. That's quite strong.
It is, but it highlights how important that critical review process is in science. Bad ideas or flawed calculations need to be identified.
It's a powerful reminder, isn't it? Even when you're chasing these huge, beautiful ideas like a unified theory, the nuts and bolts have to be right. The math has to work, and it has to match what we actually see.
Absolutely, rigor matters. This whole deep dive into her review really showcases that self-correcting aspect of science. Ideas get proposed, they get scrutinized, tested against math, tested against experiment.
And sometimes, like it seems here, they just don't hold up to that scrutiny.
Exactly.
And then, just to lighten the mood after all that heavy physics critique, Hossenfelder apparently ends the article with an ad.
Yeah, it's quite funny. She pivots straight from dissecting tensor calculus errors to promoting the Novium hover pen. Apollo edition, no less.
A floating pen.
Yeah.
That's quite the gear shift.
It certainly is a little moment of commercial reality
And
after the abstract heights of theoretical
yeah.
physics.
Well, wrapping this up, it seems the grand quest for a unified field theory goes on.
Sure.
This particular attempt, based on Hossenfelder's review, looks like a dead end because of, well, a lot of basic problems.
It really underscores the need for solid foundations, mathematically and physically.
Absolutely. And it really makes you think, doesn't it? This kind of intense scrutiny. What other areas of science, maybe things we think are pretty settled, might reveal unexpected twists if we looked that closely again? Something to ponder.